Hello everyone, my name is Bagus Hanindhito. I'm a PhD student at UT Austin. I would like to present our works, GAPS, GPU acceleration of PDE solver for wave simulation. So this project is collaboration between UT Electrical Computer Engineering departments with the ExxonMobil Research and Engineering Company. And this presentation is divided into 10 sections. And without further ado, let's start with the introduction itself. So the problem that we would like to address in our work is related to the realistic large-scale simulation of wave-type equations. This kind of simulation have many industrial applications, and it usually involves vast amount of data. Some of the notable applications are seismic hazard mitigation, oil and gas explorations, and Earth subsurface survey. And the key bottleneck in performance is data movement and communication, just like what most of the HPC applications suffer. And the important note is that the simulation algorithms and the configuration of geometry impacts the computational efficiency of this type of simulation. So the objective on our work is that we would like to investigate the performance of seismic wave simulation on modern GPUs. Specifically, we are interested with the discontinuous Galerkin discretization with Gauss-Lobet-John integration schemes on straight-phase hexahedral elements in wave simulations. Our main contributions in our work is that we are developing gaps for wave simulation in GPUs, and the development is used hardware-informed algorithms and mesh configurations in such way that we can exploit available parallelisms and achieve significant speed up over CPUs. And then we characterize and identify the key bottlenecks of GPU kernels for developing data flow aware optimizations. And then to support a large realistic size problems, we extend the scalability of our wave simulators to support multi-GPU in multi-nodes HPC clusters to achieve perfect wave scale. Next, the background. So the full wave field inversion is the state-of-the-art methods to estimate material properties of the Earth's subsurface. So seismic waves is generated artificially using seismic wave sources on the ship, for example, and these generated waves travel through the unknown mediums. As they travel, they change their amplitudes and direction because of the subsurface formations that consist of different materials, and then we record the reflected waves using hydrophones. And based off the data that we gather, and then using the approximate physics models, we can estimate the subsurface formation. And remember that this is an iterative process, and because of the large amount of data that is involved in this iterative process, it is not possible to do before the advance of petascale computing system. And there are two wave equations that we would like to simulate in our wave simulators. But of course, our work can be extended into electromagnetic wave equations and anything else that use wave equations. So the first one is the acoustic wave equations that models the propagation of compressional waves in fluids, air, earth, body tissues, and etc. While the second one is the elastic wave equations that give more detailed models for zero waves within the earth and elastic solids. So you can say that acoustic wave equation is just a subset of elastic wave equation. And discretization algorithms for our wave simulation is used using a DG. So remember that the key bottleneck is communication, and DG has lower communication costs compared to the finite difference methods and spectral element methods. There is also robust and stable algorithms that are recently developed for DG to handle non-conforming mass. And also we believe DG has better chance of harnessing the modern GPUs with highly parallel computing architectures. Second one, we coupled DG with Gauss-Lobato joint integration scenes on straight-faced hexahedral elements. This gives us two advantages. First, reduce the total number of required blast operations. And second, we simplify the blast operation into level 1 blast. So now we don't do the matrix multiplication, but we do factor multiplication. With GLL, computing derivative and interpolation at its spatial direction decouples from other directions. Let's move to the methods itself. So the methods of the code development itself start with the CPU code. So the CPU code is built, it's developed to verify accuracy against analytical solutions. After it is verified correctly, we move to develop the GPU codes or gaps. So basically we try to extract as much as parallelism as possible and maps this parallelism into GPUs while maintaining the numerical accuracy. Then we profile this baseline implementation, and the result of profiling is used to do optimization of performance to get even more faster speed up over CPU. And then to support large problem size, we extend gaps to use multi-GPU with multi-nodes HPC clusters. We use two kind of platforms, the x86 platforms, which has the two NVIDIA V100 PCIe GPUs. It is mainly used for single GPU development, while the Power9 based platform is used for multi-GPU, multi-nodes code development because it has 4 NVIDIA V100 SXM2 with NVLink in each node, and we have 128 nodes available. And each node is connected with Mellanox EDR InfiniBand. The assessment of the performance of our GPU wave simulation is done by creating 6 wave simulators configurations. This includes the combination of acoustic elastic problems, central Riemann flux solver, and single or double precision. We also prepare 3 levels of optimization in our GPU code: the baseline, the fused kernel plus LUT-based neighbor lookup and node search, fused kernel and LUT-based neighbor lookup and node search, plus the shared memory utilization. We also provide a roof-light analysis to characterize its GPU kernels. Let's begin with CPU implementation first before we go into the GPU one. So our CPU code use P4is to generate and partition the non-conforming mesh. And the mesh is built at the beginning of simulation, and we guarantee that the mesh will remain the same throughout the simulation. Because of the spatial discretization of the mesh, we have multiple numbers of elements, and the finer of the finer the mesh, the higher number of elements will be. And this is the elements and the element database. So an elements basically units of the result of discretization, and then element has several nodes in which we perform a volume and flux computation. In gaps, we represent this element using a class called element database. So this class contains arrays of variables, contributions, materials, and etc. This is the size of each elements that depends on the problem size, the precision that is used, and the number of nodes. In our simulation, we mostly use 512 nodes per element because it provides a good number that is hardware friendly, and also it provides adequate resolution to reduce the dispersion error. For the data flow itself, there are three major simulation kernels: volume, flux, and integration. So volume computation is completely interior computation. Each element can be computed independently, while the flux computation needs neighboring element phase data. So there is some kind of communication between the element before flux can be computed. The last thing is the integration, which is the very small kernel. So the integration will integrate the sum of contributions, that is the volume contribution and flux contributions, to update the variables. And our simulation flow consists of two main simulation loops. The inner loops is the integrator loops using the LSRK4. There are 5 integration loops for each time steps. And then the outer loops is the time step loop. Ghost exchange happens when we use multi-CPU for simulations. So during the flux computation, there is a case that the neighboring elements are located on different CPUs. In that way, we need to perform a data transfer between CPUs so that the flux computation can be performed. And we call these neighboring elements that are located on different CPU as a ghost elements. And ghost exchange is done mainly to exchange the ghost elements, and it is done using the two kind of arrays, the ghost layers and the ghost buffers. Okay, now let's move to the single GPU implementation. So basic single GPU implementation still use P4is to generate and partition the mesh. Then instead of operating directly on the mesh, we copy the mesh structures to GPU memory at the beginning of the simulations, and we use the custom mesh handling method on GPU. We launch the GPU kernels in the simulation loop instead of calling a methods on CPU. And then at the end of the simulation, we copy back the result into CPU memory. So there are 3 GPU kernel: the volume kernel, which is a very much a local operation, and it has a compute intensive GPU kernels. Flux kernel, which is not completely local because it needs neighboring elements data. It is also the most inefficient kernel because of the branches that is needed to determine which elements is neighboring with each element at which phases. And the shortest kernel is the integration kernels, and memory accesses are dominating these integration kernels. Finally, the data structures need to be changed. So P4is used tree-like linked list to manage and handling the mesh. So pointer operation is used to determine which elements is neighboring which elements. But sadly, the pointer operation is not GPU friendly, so that we use array instead of linked list in GPU to store all of the element database in GPU memory. That way, fast accesses and easy for extracting the data level parallelisms. But because we eliminate the ability to infer the neighboring elements using pointer operations, we need to develop our custom method to find out which elements neighboring with which elements. So the basic implementation itself is not that efficient because the iterative methods, but we will replace this method with more efficient LUT-based neighboring lookup on the more optimized GPU implementation. Secondly, we need to handling phase nodes. So there are data hazard, especially for nodes that are located on the edge or on the corner of the elements, because these nodes has multiple phases. So the solution is that we serialize the flux computation phase one by one. Then we need methods to find which nodes located on which phases. So we develop these methods, but it's not that efficient. So we will replace these methods with a LUT-based, just like the one that we are using for neighboring lookup. We also perform some basic optimization, such as pre-compute repeatedly use values and store it in the constant memory in GPUs. And also we do a loop refactoring and unrolling to reduce branches or different changes. Now we have a basic GPU implementation. So we profile our basic GPU implementation to see which bottlenecks that limits our performance. Based on that, most of the performance limitation comes from the memory bounded nature of these wave simulators, even with 1 terabytes per second of HBM2 memory bandwidth. And we perform a kernel fusions of the GPU kernels so that we can keep the state of the streaming multiprocessors throughout the kernel execution. Because we keep the state of the SMs, we can reduce the need to fetch data from global memory, reducing the data movement even further. So the candidate for kernel fusion is volume and flux, but to do that, we need to modify flux a little bit. So we spare internal flux with external flux. So the internal flux is the one that does not require ghost exchange, while the external flux will definitely need to wait until the ghost exchange is finished. So in that way, we combine compute volume and internal flux, give more time for overlapping ghost exchange, and then after the ghost exchange finished, we can do the external flux computation. Unfortunately, fusing integration kernel is difficult due to data hazard. So integration kernel will update the variables. We have to make sure that all of the contributions in all elements has been computed before all variables is updated. This requires a grid level synchronization, and it is implicitly done with spared kernel launch. So LUT-based neighbor search basically just consists of two arrays. The first one stores the index to the element arrays, if local elements, or to the ghost layer if it is ghost element. The second array stores the properties of the neighboring elements, whether it is a local element, whether it is a ghost element, or whether it does not have neighbor because it's located on the boundary of the problem domain. And these LUT are constructed once at the beginning of the simulation and copied to GPU memory. LUT-based node search is used to find out which nodes located on which faces, and it consists of 8-bit integers. And it is stored on GPU constant memory. Shared memory is very fast user managed on chip memory, but because it's in Volta architectures and newer architectures, shared memory and L1 cache are fused together. So we need to find out which data that are worth to store in shared memory. So there are two candidates of data, the contribution and variables, but for variables, it will complicate memory accesses. So we go with contribution. So we store the contribution on shared memory. We also try to schedule multiple thread blocks inside an SM so that the SM can switch to another thread blocks to hide memory access latency. But then we need to control the number of registers that each thread block consumes. We use the NVCC launch bounds command to instruct the NVCC to limit the register usage so that one SM can handle multiple thread blocks. So let's move to multi-GPU implementation. So basically, we still use P4's libraries, but because it does not support GPUs and we don't want to build the libraries from scratch, we still generate partition and distribute mass on CPUs, and one MPI process handles one GPU so that the process is still remain the same as the single GPU's implementation, except that ghost exchange is done in GPU instead of CPUs. To do that, we need a CUDA-aware MPI so that this MPI can send and receive the memory buffers in GPU without staging first on CPU memory. And CUDA-aware MPI supports NVIDIA GPU direct technologies such as the P2P and RDMA. So we move ghost layer and ghost buffer to GPU memory to facilitate multi-GPU ghost exchange. And we need the special GPU kernel to update the ghost buffer before the ghost exchange is initiated. and the received data from Ghost Exchange is directly stored in GPU Ghost layer. We also optimize the size of the data that need to be sent during Ghost Exchange so that it can lower the communication cost overhead. Last thing is that in MPI standard, non-blocking semantics do not guarantee asynchronous progression. So we try to use MPI libraries that support asynchronous progression if explicitly enabled, such as MFAPage and Spectrum MPI. In that way, additional thread is created for communications and provides better overlap between computation and communications. So let's go with the evaluations. CPU2 has an average speed up of 1.36 over CPU1, and the Ghost Exchange account for 9.5% and 17% for CPU1 and CPU2 respectively. Asynchronous progression is not helpful for CPU run because of the oversubscription. Remember that asynchronous progression spawn another helper threads for communication, and there's total threads exceed the available physical cores on CPUs. It's average speed up of the GPU implementation compared to CPU1. So the baseline has a speed up of 45.67 times compared to the CPU1, while the FL has a speed up of 69.30 times compared to CPU1. And the most optimized GPU version, the FLS, has a speed up of 84.15 times compared to CPU1. In that way, the fused kernel and LUT neighbor search and node lookup give a significant improvement over the GPU baseline implementation of 1.74x average speed up. Meanwhile, the FLS give another 1.117x over GAPS FL in terms of speed up. We use NVProf to gather memory transactions and create this offline chart. So most of the kernels are memory bound, and by fusing volume and flux kernels, we move the combined kernel to the top and right of their original positions, which means that it has more gigaflops per second and it has more flops per byte, which is good. The use of shared memories also move the kernels to the top, which means that it has higher gigaflops per second, but it has moved a little bit to the left because it has now reduced L1 cache capacity. And high order discretization, meaning that elements with higher number of nodes are favored in many wave simulation due to their ability to limit dispersion error. So we would like to know whether we have an advantage in hardware perspective if we use high order discretization. So we have two configurations of the mesh, one with elements that has 64 nodes, one with elements that has 512 nodes. We keep the aggregate number of the nodes the same, around 63 million. And it is shown that the mesh configuration with elements that has 512 nodes is 1.12x faster than the one with 64 nodes per element. The reason is that the 64 nodes per element has more flux computation than 512 nodes per element, meaning that it has more, it has less local computation compared to the local computation, which limits the performance. Therefore, we can conclude that high order discretization is also beneficial from hardware perspective because of better locality. Now we also have reduced the amount of Ghost Exchange data that need to be sent. So by identifying the data that does not need to be sent during Ghost Exchange, we can reduce the communication overhead significantly. And we try to reduce this ghost element to 27% of its original size. And by reducing these ghost elements, we can reduce the communication overhead by 72 75.81% and 75.83% for intranode and internode ghost exchange. Now the MPI asynchronous progress impacts. So we try to overlaps communication with computation, and thanks to the asynchronous progress support in MPI libraries, we can do overlapping better. So first one, we have the MVPage GDR configured without asynchronous progress, and MVPage GDR configured with asynchronous progress enabled. With asynchronous progress enabled, it can reduce the communication overhead by 56.74% in average, which is a huge number. In single node run, although Spectrum MPI with asynchronous progress enabled has an average of 51.27% less communication overhead compared to the MVPage GDR with asynchronous progress enabled. Unfortunately, in the multi-nodes run, Spectrum MPI fall with asynchronous progression falls behind the MVPage GDR with asynchronous progressions. The reason is that the Spectrum MPI has inefficiency in InfiniBand multi-rail utilization. So overall, asynchronous progress improves the ability to overlap the ghost exchange with volume and internal flux computation. And we also investigate our wave simulator scalability. So as we increase the number of GPUs, we increase the problem size as well. So the number of elements handled by each GPU remains constant. And as you can see here, our simulators achieve weak scaling over 128 GPUs on 32 compute nodes for both single precision and double precision runs. So the future works, we plan to address the data movement because that's what limits the performance of our wave simulation. To reduce intra-device data movement, we try to explore better ways to use shared memory in order to reduce data movement. We also want to experimenting with the new CUDA programming model called cooperative groups so that we can better organize the threads to extract parallelism from our workload. We also want to reduce the inter-device data movement, so we try to send only nodes located on the face, but it will complicate the indexing a little bit, so it will add a slight computation overhead to index the nodes. Secondly, we try to use mixed precision, so we use lower precision for communication and higher precision for computation, in order to reduce communication overhead while maintaining the numerical stability. So the conclusions, we explored the performance of class of waveform simulation. Specifically, the unique in our work is that the use of the G finite element methods along with GLL integration schemes on hexahedral elements with straight faces. It has lower arithmetic intensity compared to simulation that use general meshes. This way, it is very hard to attain peak performance of GPUs because of the excessive data movement and very few computation to overlap with communication. We also deployed several optimization for GPU kernels, and it yields satisfactory improvements compared to the basic GPU implementations. The kernel fusion and LUT-based neighbor node lookup yield up to 2.6 times speed up over baseline GPUs, while the improved shared memory usage and SM-aware register allocation at up to 1.49x additional speed up. We also considered strategies to reduce intra and internode communication by reducing the data sets that needs to be ghost exchanged, and also by using MPI libraries that support asynchronous progression. That way, we can achieve weak scaling over 128 GPUs and beyond. Thank you very much for your attention. I hope my presentation can explain clearly on the work that we are currently doing. And this research was supported by ExxonMobil Technology and Engineering, National Science Foundation, and computational resources from Texas Advanced Computing Center or TEC. Thank you so much for your attention. Hope to see you